Hello everyone, and welcome to another video where we will be creating a project using 4D systems displays. Today I will be using the ulcd 480 round display with capacitive touch and cover lens bezel to make a smart timer. The smart timer will be controlled by a rotary encoder and dial. Let's get started. So same as last time, I've just written down a quick form breakdown just to plan out what I want to actually happen on the screen. I'm keeping things a bit more minimal this time with fewer features, just making the project clean and functional. However, what's important is the interaction that happens between the user and the product. So form 0 is the main setup screen. This is where I'll have a smart knob with values 0 to 60 to set up a time up to 60 minutes. It'll be controlled by a rotary encoder, and while I haven't fully figured out the physical housing design yet, we'll get to that after the coding is done. There'll also be a button to switch to the next form, which is form 1, where the actual timer lives. So this timer is going to be drawn manually through code. The timer is going to take the value from the knob and start a countdown timer from that value, meaning if we set it to 30 minutes, the timer will start at 30 minutes and count down to 0. And then there will be a button to take you back to form 0 and restart the loop. That's really all I need for this device. The most important thing is making sure that the rotary encoder is working properly to control that smart knob. So to get that working, we need to check the available GPIO pins on the breakout board. If you go to the 4D Systems website, you'll find pin mapping tables depending on your board. My breakout board that I'm using is the 4D UPA. Now if I open the data sheet and come down to these charts here, it actually shows me what GPIO I should be using in relation to the screen's processor. So this is something really important to take note of. In my case, CLK is connected to pin 2, DT is connected to pin 3, and I'm not using the SW pin, which is the push button on the rotary, so I'll just ignore that. So I actually just soldered some female and male pins onto the breakout board, just so I could use jumper wires and have easy access to those GPIO pins. Of course, if you want to, you can also solder your wires directly onto the breakout board. However, I thought this would be easier for my testing and debugging. Once everything is hooked up to the breakout board, we can jump into workshop 4 and start coding. Okay, so now that all of that's set up, just like last time, I'm going to choose my display. I'm going to keep it in the same orientation, press next, and then I'm going to choose the ViSi-Genie environment. So the first thing I'm going to do is build the smart knob. If you go to the File tab, and then Samples, and Smart Knobs and Gauges, you'll actually see that there's a bunch of pre-made graphics that you can use in your projects. I'm using a set of them, but I decided to edit the faceplate to be circular. I just thought this looked way cleaner on the ulcd 480 round display. Here's how I set up the smart knob. First, I insert the base image, which is the blank knob face. On layer 1, I add the arrow graphic. I set its max value to 60 so it lines up with the minutes. This means that we'll have 60 frames throughout our animation, but it also means that each click of the knob is equal to a value from 0 to 60. And that lines up with the minutes. I want to be able to set a time from 0 to 60 minutes. I set the reference point to center, realign it, and set the rotation to 270 degrees. Then on layer 2 I add the half gray gauge and the half colored gauge. We're also going to set the max value on this frame to 60. Other than that, you don't need to touch it. On layer 3 I insert another color gauge, again with a max value of 60, but this time I'm going to make the degrees -135 and 135. Finally, on the bottom layer, I add the full gray gauge. This is going to sit behind everything and gives it that inactive look when the knob hasn't moved yet. To make things clearer for the user, I'm going to add a numeric object that shows the exact value that is being selected by the knob. Once that's done, I hit OK in the Smart Widget Editor. And super important, in the Properties tab, make sure you set the minimum and maximum degrees to 45 and 315. If you don't do this, the knob won't work properly. Now that our knob is finished, I'm also just going to drag a background color in, just to make the screen look a little bit more full. I'm going to change the start color to a blue to match the color of our knob. And then if you click on the smart knob, its black background will disappear and only leave the colored background that we just inserted. Then I'm just going to drag in a button, resize it, and change its on-change event to form 1 activate. If you don't want to use touch for the screen and purely want the interaction to be with the dial and rotary encoder, then instead of the smart knob, you can change this to a smart gauge and it will function in the same way. It just means that you will be unable to interact with it through touch on the display. So here on form 1 is where we're going to build our timer. The first thing I'm going to do is copy and paste our button from form 0. Except on this page, I'll change the on activate to form 0 activate. So once our timer is done, we can press this button and go back to set a new time. Then I'm going to drag in an LED digits widget. I'll make the decimals 0 and the digits 2. We're going to use 2 of these digits to make the minutes and time on this timer. I'm just going to resize it and copy it over. So I'm just going to change the color of this to white just so it's easier to read on the screen. You can change it to whatever you like though. Then if we head over to primitives, I can drag in a circle. Again, I'm going to make it blue to match the rest of our design. And I'm going to make the radius smaller. So now we can use them as the little colon between the minutes and seconds. So now that all of our widgets and the visual elements of our design are ready, the only thing that's left to do is write the code for this display. So for our code, we'll need 1 magic event that we linked our knob to, and 4 magic codes, which I will run you through now. So in our global section, we first set a constant called input pullup to the value 2. It's used later to enable pull-up resistors for our rotary encoder pins. This is a standard setup when using mechanical encoders. Then we set our variables, those being knob value, which stores the current value of the rotary encoder, basically how many minutes the user has selected. Previous CLK and current CLK are used to track the changes on the encoder's CLK pin. These values let us detect when the knob has been rotated, and DT state holds the current state of the DT pin, which tells us which direction the knob is being turned, either increasing or decreasing in value. The last 2 variables we have here are what we use for the actual countdown timer, how many minutes and seconds are remaining as the timer runs. Then in our pre-Genie initiation section, we configure our rotary encoder pins. Pin set 02 sets GPIO pin 2 to be an input, which is connected to the CLK pin on the rotary encoder. Pin set 03 does the same thing for GPIO pin 3, which is connected to the DT pin. Then pin high 2 and 3. These lines apply internal pull-up resistors to both pins. This ensures a stable high signal when the encoder is not being turned, helping prevent random noise or glitches in the input. Then finally, we read the initial state of the CLK pin and store it in previous CLK, which is important for comparing later to detect changes. In the main loop, we're constantly reading the current values of the CLK and DT pins. So current CLK is compared to the previous CLK value to detect the rotation, and DT state helps determine the direction of the location, that being left or right. Then this condition checks for a rising edge on the CLK pin, meaning the encoder was just turned. If true, it means the knob has moved. Here, if DT is low when CLK rises, that means the encoder is turning clockwise, so we increase in value. Otherwise, it's going counterclockwise and we decrease in value. The next 2 lines clamp the knob value to stay within the range of 0 to 60. No negative minutes and nothing over 60 like values like 70, 80 and so on. Then we update the 2 widgets. The smart knob is the smart knob on form 0. This animates visually with the current value, and T LED digits with the index 0 refers to the minute LED digit. This lets the user see what they've selected. Finally, we store the current CLK value as the new previous CLK, so we're ready for the next rotation check. Now in the countdown timer logic, we check whether our 1 second timer has expired, meaning it's time to update the countdown, and if both minutes and seconds are at 0, the timer is done. If seconds hit 0 but minutes aren't finished yet, we reduce minutes by 1 and reset seconds to 59. This keeps the countdown accurate. If seconds aren't 0, we just decrease them by 1 like a normal countdown. Then finally, we just update the 2 LED digit widgets with index 0 for minutes and index 1 for seconds. These show the current countdown time on the screen. In our last MagicCode, MagicCode 3, which is our post-activate form, as soon as the user enters form 1, the timer screen, we take whatever value was set on the knob and store it as our minutes. Seconds are always reset to 0. Again, we update both the LED digits with the initial countdown values, and finally we start the countdown, kicking off the 1 second loop. So that is how this project works. The rotary encoder handles user input, the LED digits give real-time feedback, and the timer logic runs a consistent 1 second countdown. And everything is handled here in the ViSi-Genie environment using MagicCode. So it's super clean and easy to use, and it's also very easy to expand on if you want to add more features to this project later. So now that the program's working, it's time to start thinking about the physical design. The main things I had to consider when designing the housing were the user interaction and the internal space for the components. Here, as you can see on my really bad drawing, originally I wanted the rotary encoder to sit centrally with a dial going around the outside of the display. But that caused a major problem, being that there was nowhere for the breakout board and ribbon cable to escape to out of the body. So I came up with a better system that kept the inner body hollow, so the components had space to sit without blocking each other. I started by drawing the main shape, shelling it, and cutting out the screen hole. Quick tip is if you download the step file for your display from the 4D website, you can just offset the PCB's perimeter tolerance. I used a 0.6mm offset and the fit was perfect. Then I added a platform for the rotary encoder at an angle, a few internal mounting blocks for the electronics, and then we got to the part where it got fun. I made a large gear that sat at a wider diameter than the body. Then I extruded the outer dial using that gear's teeth. This put the gear teeth on the inside of the outer ring. Next, I made a smaller 34 tooth gear with a central hole that matched the rotary encoder shaft. I made sure the fit was tight enough so it wouldn't slip, and thanks to this gear system, the rotary encoder could be offset rather than sitting in the center and still control the dial smoothly. So this is what the final internals look like. I checked all my tolerances and sent the parts off to print. The final assembly is made of 3 main parts, that being the main inner body, the large outer dial with the internal teeth, and the small inner gear that connects to the rotary shaft. From there, it was just a matter of putting everything all together. Thank you again for watching, and I hope you were able to learn something about our Workshop 4 environment through this video. Here's the final product.